we were talking about this code and implementation of UNET. In the previous hour, we went over UNET theoretically. We've talked about the differences of UNET with respect to classification networks such as AlexNet. AlexNet was a convolutional plus fully connected classification network. However, UNET was a fully convolutional neural network. And the important outcome of this fact was UNET could accept any input size, unlike AlexNet. And we've seen that the reason was the fully connected layers. And since we knew the architecture of UNET, we have gone over this PyTorch code where the UNET architecture is being realized, operationalized, and how it's done. You've already gone over similar things in your lab sessions, and you know how PyTorch creates a graph, but this was another implementation of it, or maybe, and it was a relatively I don't know, complex implementation because it's a complex architecture. And somehow these classes realize the network. We've gone over these layers, and actually we have many things that, I mean, what I recommend you is, in order to understand an architecture like UNET, which is a simple architecture, you can just go over this code. I'm going to share this code with you, but this is not my code. This part is not my code. The other parts are mine, but the architecture is not mine. And the moral of the story about the architecture being not mine was, I could replace this architecture with any other one. People do comparative studies in their papers. How they do it is they find these networks from GitHub and they just make a comparison. They run the same experiment code over these architectures. That was what we talked. Now, this is the main experiment code. What I'm experimenting here is I have a simple data set of some satellite images. I'm going to feed them to UNET, and I'm going to train the UNET with some data. For this example, I have specifically chosen some images and some labels which are in a different formats than PyTorch can, naturally understand. Because this is, I've taken this from the DSTL dataset. What DSTL dataset is? DSTL dataset is this guy. DSTL dataset. It's a Kaggle challenge. It's a data. We've worked on this problem some time ago. It's a large image. The resolution of the image is very large. It's like it has 25 images on the data set, but they are very large in resolution, like 3000 by 3000 kind of. What I did was, I'm not going to show you that part. In some other environment, somebody did this for me. They've cut these images into small pieces, like a grid, small pieces. Okay, small pieces. Where each piece is 224 by 224 by 3 RGB images. Okay, so out of 25 of these images of this grid, I had more than 5,000 224 by 224 images. Why am I showing you this example? This is what happens. This is what happens in real life. In real life, you could be working on any problem. You could be working on satellite images. You could be working on sound, or you could be working on some medical data. Maybe somebody collects some ECG signals, and they are in some format. You're going to create your own data set. How to feed an arbitrary data set to a convolutional neural network? Because theoretically, you know how to do this. Theoretically, you know that there's these layers and you feed those values to these layers, but how to do it in real life? So I think the most valuable practical the most valuable practice of this session will be understanding how an arbitrary signal can be fed to a PyTorch deep neural network architecture. So what I have is, I'm going to talk about my data. Having done this, I created some RGB images, and surprise, surprise, I've used MATLAB to do that, because the student who did this was using MATLAB, and they created this. So that student, if you load it to the workspace, it creates this input batch, and this, when you load it, it has an input batch object, which is 224 by 224 by 3, unsigned integer, 16 values, which means if you look at inside it, it is an image, it's an RGB image where pixel values are 16-bit depth. So each pixel value has, each pixel has some values between 0 to 216 minus 1. Okay, so 260 minus 1 is something 65,000 something. Okay, so it's between these values. So, okay, I've put them into these files. So each one of them is this, the format is the same. If you load another one, it is another one. So the values have changed because that's another file. That's how I did this. You could have done it differently, but this is a practice, because manipulating some foreign signals in MATLAB and creating these mat files is something easy, but you don't have to do this. These could be some Excel files, or these could be some text files. I'm using this because these are satellite images, and sometimes I want to visualize them, and visualizing things in MATLAB is very easy. So just like I told you before, in my deep learning experiments, I'm using Python and PyTorch, but when I'm trying to analyze a signal, I'm using MATLAB. Because I'm accustomed to it, considering my electrical engineering background, but it could be something else for you. Some people are all using only Python, the others using other things, doesn't matter. This is the nature of my data. It's an arbitrary data. These are the signals, and actually in my data set, for each image, I have some labels. So these are the ground truths. So for the first image, I have this logical ground truth. Some values are 1, some values are 0, and it has the same spatial dimensions. Actually, these values are the locations of trees. Tree, as we know it. I mean, a tree is like a tree, I mean, ağaç in Turkish. So I have a satellite image of this size RGB. The regions, which are the pixels which belong to a tree, are labeled as 1 in my mask. So this will be when I train it. This will be when I train it. This will be a network which is capable of finding the pixels that belong to a tree. Well, good practice. Actually, we had some under review study on tree detection using deep neural networks. So that's I've kind of compiled this simple project out of those studies. Anyways, and that data belongs there as well. So I won't be able to share the data, guys, but I'm going to share all the codes so that you can just change this code and manipulate it the way you want to. Okay, so that's my data. I'm going to be training the UNET over this data. What are the steps? Let's look at the steps. This is my main code. So in Python, you can create a main code and run that main code like this, you know. So that's a single main function. It's calling other functions and other classes. I'm going to show those files when I get there in the code. Okay, the first thing I do here in my code is I'm checking if I have a GPU. I have to do this because I want this code to run in a computer where there is a GPU and where there is no GPU. So it first detects the GPU. If there is a GPU device available, it gives the GPU device's name. So it is like GTX 5000 kind of, and it prints it on the screen. If there is none, it says that there is no GPU. And depending on the device, it decides on the device object. Because this device object is important for us, PyTorch will use this object to do the training and the inference stuff. And so we are going to tell PyTorch that we will be using this device, whether it's a GPU or a CPU. Actually, all my deep learning code starts with this because I want them to run on my home computer where there's no GPU, or my desktop computer where there's no GPU, or on my server where I do the experiments where I have a GPU. Okay, second part, my parameters. So in this experiment, I'm going to be using this training set. As you can see, the training set has 64 items. I have 64 images. Actually, the real image set that I told you has more than 5,000, but to make the example simple and trainable in this hour, in this live code, I've picked 64 of them only. So the training set size will be 16 of these 64. I can make this something between, I can make this 64 as well, but I want the network to be trained very fast. I'm going to set this value to 16 so that I'm going to be using the 60. So the command is not right. All the training set, all the sets, training, validation, and test will sum up to 16, okay? And I'm going to be applying cross-validation, guys. We talked about cross-validation, but I'm going to remind you. Cross-validation means you have an entire set, which has n number of values. In my case, it is 60. I'm going to be using some of them as training. So this part will be training set. Training. Some of them for testing. And I'm going to be using some of the training for validation. Okay? Because validation is a part of the training where we use it for hyperparameter tuning, remember? So actually, in cross-validation, when you do this for a single fold, for example, let's say I'm going to be using 3/4 of the entire set for training and 1/4 for testing. This is called a 4-fold cross-validation because I'm using only 1/4 for the testing. To be able to test the entire set, I'll have to repeat the experiments 4 times where this test set will correspond to different quarters of the test set so that I cover the entire set for testing in 4 experiments. This is called a 4-fold cross-validation experiment. And in general, it's called an n-fold cross-validation experiment, where this case, and let's say, that's not a k-fold, let's say, k-fold cross-validation experiment, where k is 4, okay? And actually, here, I decide the number of folds for my cross-validation experiment, because in the following lines, I'm going to be calling a cross-validation function here. It's going to create me the folds. So when I say fold number 1 out of fold number 4, it's going to give me this set. When I call the same function with fold number 2 and fold size 4, it's going to give me the other part, which has no intersection, where the test sets have no intersection. So that by using that function, I could repeat the experiments to complete my cross-validation set. There are ways to do this in different frameworks. In PyTorch, there are codes to do this. The PyTorch can automatically create these validation sets and stuff. I will use them. I've written my own codes. Why? There were some reasons for that. You may have some reasons. In my reason was some of the experiments were run in parallel by some people, other people in MATLAB, and we needed to use the same experiments. We needed use the same training set so that our cross-validation experiment was identical. That's why, to make our experiments similar to them, because this was a collaborative study with some people from Germany, we had to use a cross-validation code which was identical to theirs. Okay, So this is my parameters. This is saying I'm using cross-validation. A K equals 4 cross-validation, 4-fold cross-validation. And I'm going to be using the first fold for this experiment. Okay. These are the parameters for the training. Remember, in training, you have 16 mini batches. If you have 16 mini batches, and if the entire training set is 16, one epoch will only take one iteration. This was a question from the midterm some of you could do, so I hope you'll understand it this time. So if I select the mini batch size for as 8, then one epoch will be equal to 2 iterations because 16 over 8. Okay, good. These are the training. So number of epochs, how many epochs that I'm going to run, the learning rate, the step size and gamma is for the learning drop. I'm going to be dropping the learning rate by this amount every 5 epochs. I'm going to show you how. These are training parameters, and this is my input image size. This network can accept any kind of value, but I need this value because
Hocam bir şey sorabilir miyim?
Please.
Türkçe soracağım. Çizimden soracaktım da. Neyse. Şimdi hocam biz burada 4 fold var dedik ya. Ya ben şöyle anladım ve biliyordum da ben karıştırıyorum. Şimdi mesela training datasında diyelim. Training datasını ben kendi içinde 4 parçaya bölüyorum. Her bir parçasını validation için kullanıyorum. Kalan 3 parçasını training için kullanıyorum. Sonra kullandığım parçayı değiştiriyorum. İşte birinci, ikinci, üçüncü, dördüncü gibi. Sonra bunun işte belki ortalamasını alıp bakıyorum gibi. Buradaki fold benim training datasını kaça böldüğümü gösteriyor değil mi?
Well, yes. In your example, your friend is asking another practice of the fold, and she's asking, well, in her experience, in cross-validation, what she did was she divided only the entire training set into K folds and changed the validation part. Okay, that's a practice. That was not what I told you. So you're asking why they're different. Am I correct?
Yes.
Okay. So, Ece, is it you? If I recognize your voice correctly.
Yes.
Okay, Ece, in that case, I mean, we are talking about a statistical experiment. In that case, you are not changing the test set, if I understand correctly. I mean, if you don't change the test set, there is a problem about this statistical experiment. Maybe you have selected your test set from the easy samples in your entire set. How are you going to defend that?
Ama böyle olursa test seti training'de görüp biraz cheating yapmış gibi olmayacak.
Well, no, we are not using the test set in the training. So let me just repeat it again. In this experiment, in this experiment one, in the experiment I'm going to run, I'm using only these for the training. I'm not using this for the testing, okay? This is fold 1. It was an experiment. In experiment 2, I'm using this part for testing, the other parts for training, and this part is trained from scratch. And for the first experiment, I have some accuracies, 0.7. For the second, 0.8. For the third, 0.6. For the fourth, 0.5. None of these experiments use the test set during the training. Clear?
Okay.
Okay, so I'm not cheating. Okay, are we on the same page that I'm not cheating?
Okay, I need to think about it more because in the end I need to adjust hyperparameters or weights.
Okay, okay. So about adjusting hyperparameters. For the first experiment, which was I used, so for the first, let me get back to the first experiment. where you only use the yellow lines. Okay, for the first experiment, this was the test set. You did not use this for training.
Yes.
During this test, you needed to make some hyperparameter adjustments, right? Hyperparameter adjustments were done by this validation set. So it was like you used this part for the training, you checked the validation values, didn't like them, change the parameter, trained again with this training set, check the validation set results. We didn't like it. Change another parameter, trained only with this set again, check the validation, you are satisfied. Then you go test with this test set and write your result. That's how you do it. Okay.
Okay.
So about me cheating, I guess I'm not cheating, but about you only using a single test set, well, maybe you're choosing the test set among the easy samples. Is it not that cheating? So the accusations became the opposite. I'm accusing you right now about cheating. So is it not cheating using a selected test set, not testing the entire set? Don't you think?
Yes, actually, selecting a test set is another major issue.
Yes, you're right. But when you have an entire corpus of data, I think you should be testing the entire data, because we are assuming that it represents the entire universal set. Isn't that correct?
Okay.
Okay, so
Thank you.
maybe so it became like a Game of Thrones scene. Confess your crimes. So what I'm trying to say is, in an experiment, statistical experiment, test set all the data should be tested in different folds, but the test set should never be used during training. So we agree on that, don't we?
Yes.
Okay, thank you very much.
Hocam,
Please.
sorry, I'm confused too. I thought we were only folding the validation and the training set, but the test set is something exclusive, that separate set. We don't,
We don't
neural
use the
network
different-
never met it.
Well, actually, we are not using it during the training, guys. So that's really true. I'm not changing that. That's cheating. We are not doing that. For the first fold, we are using the test set and the validation set, test set. We are not using the test set during training. We are using this for training, and we are using the validation values for getting an idea about how the network works, to choose a parameter value. You can change the place of the validation set. Okay, I understand that. It would mean folding the validation set within the training set. Okay, but still, after this experiment, you have only tested this part of the entire set. Don't you want to test this part as well? Maybe these parts you selected from the universal set were easy examples. Don't you want to test this part as well? Olmadı mı?
Hocam ben de biraz bakayım, benim de kafam karıştı.
Okay, the second question was from Melek.
Evet hocam.
Okay, you can fold the validation set, and that would mean something statistical, meaningful, because you are trying to find the correct parameters for your training, right? So checking different parts of the training set for validation and deciding the parameters accordingly is meaningful. But that's another fold. What I'm trying to say is, you want to test the entire set. What are you going to do?
Okay, so
please.
We are doing exclusive experiments,
Yes.
and we take their average, right?
Yes, if that's what you want to do. I mean, when I'm doing experiments on an entire set, that's what I do. And that's
to provide a more homogeneous data set, I guess.
Yes, I mean, the data sets are usually not homogeneous and not balanced. I mean, if I take this satellite data set, for example, I'm looking at part of a lake, then I'm looking at part of a forest. I mean, testing only the forest and testing only the lake will give me different results.
Okay, thank you.
That's what we do usually. I mean, what I do is usually I randomize all the samples. After randomization, I take the folds. I do my best to make it, but in the end, I fold the test sets, but never use the test set during training. Guys, are we clear on the fact that we never use the test set during training? Okay.
Train of this question.
Okay, Cameron, you've got a question?
Yeah. So after we change the test set, are we finding or optimizing or tuning the parameters again for the different sets?
Yes, that's a good question, and that's usually confused as well. For different exclusive experiments, just like your friend put, you can have different parameters, and that's okay.
But then which one are we going to choose at the end?
Well, that's a practical problem. That's a practical issue. About statistically assessing your success over a training set, that's acceptable. But in real world, if you're asking me which network I'm going to be using, maybe you're going to be using it ensemble networks. I don't know. I don't know how you're going to put it into practice. But for a statistical experiment, which is scientifically true, yes, for an exclusive experiment, which uses a test set of its own, you can tune its parameters independently. There's nothing wrong with that statistically. There's nothing wrong if you don't use the test set during the training set for a single exclusive experiment. Answer to your question? Wait, I did not
Actually,
answer.
no, I was asking something different.
So, what do we do in real world, you're asking?
No, actually, I think I couldn't ask it correctly, maybe. So when we look at this example, so we've got test set and the training set, and inside the training set, we have one fold for validation and the remaining two folds for training, I guess, right?
Yeah.
So we have left the test set all out, or we are not touching it?
Yes, during training, yes.
Yeah, we are training on these two folds and validating on the remaining last.
Yes.
Is that right?
Yes.
We decide on some parameters, we get some value, then change the validation to other fold, train on the other side. So in total, we do we do this 3 times, and we get 3 accuracy values or something for the.
Well, during training.
Yeah.
Well, in order for this experiment to be statistically true, you don't necessarily have to fold the validation set. I mean, your friend said that we've always fold the validation set. Folding the validation set will optimize your hyperparameter optimization procedure. And by the way, there's a point that I'd like to put. This doesn't have to be a full fold. It could be just 2% of the 2% of the training or entire training set as well. So it could be something small. It doesn't have to be an entire fold. But back to your question. So imagine you did not fold the validation set within the training set. That experiment is statistically true still, because you did not use the test set in training. However, maybe you did not get the best results. Answer to your question?
Yeah, but like if we are not changing the validation set, and I mean, what I've seen in cross validation is usually changing the validation set around, and therefore training all the data, testing all the data, and getting the most optimal, the average from it. And in the parameter tuning part, it's the same, like changing around the validation and testing which parameters give the best accuracy output.
Well,
but here we have made a different test set, and I mean, if I apply what I've seen to the training part, which has this validation 2% or whatever, okay, we did this, and we maybe did it for one fold, which means not changing the validation set, but one fold. Let's change that, because we already have fold comprehension here, which refers to test. One time, which we didn't set off validation, or maybe we did it twice. We chose some different 2% of the training data and trained it on the other section of the training data. But then Okay, like we got some value, and then what about test? Like, what are we going to achieve by changing the part of the data that's going to be used for testing in the next part of the experiment?
Okay, let me try to explain it again. The reason we are folding, if we are doing folding in the validation set, is to find the best parameters, not to find the accuracy of the experiment. Are we clear on this?
Yeah.
Okay, so you may do validation in different parts. You may fold the validation set within the training set, or you may not. The result will be you finding suboptimal parameters for this experiment. Okay?
Yeah.
When you're done with your validations, changing the validation set's position, folding it, or different parameters, in the end, this is the end of training, you come up with a set of parameters. The parameters are weights. And you say, okay, with this number of, with this learning rate, with this number of filters, I had the best results from the validation set, or a fold of validation sets, your choice. I think this experiment is over. Let me check the test set now. You test it and you get a result. Are we clear on this?
Yeah.
Okay. At this point, you're asking, why are we folding the test set? What I'm telling you is, I have an entire set. Nobody told me which part was training, which part was test. I've chosen this part to be test. Okay? And maybe this part of the entire set was the easy part. Then in that case, my accuracies for this problem over this set may look better than it should be. That's why I'm doing other sets of experiments, independent experiments, where I repeat all these operations and tuning and validation and etc. for another test set in other part of the entire set. Again, I do not use the test set for training so that I get that part of the test set as well. So folding for the test set in an experiment is this. And if you want to get real results for an entire set, that's the thing you should be doing. Because maybe you, just like I said, maybe you've chosen easy samples for the test set. In real life, in challenges, in Kaggle or international challenges, the organizers indicate the test sets themselves. They say, this is the test set, this is the training set. Okay. But if there's no indication of a specific test set or train set, what you can do is folding the test for statistical correctness. And number of folds or leave one out training, you can do anything. There's a technique in cross-validation. You take one test sample, you train with all of the others and do validation if you have time. And that's also an experiment. It is n-fold and being equal to the training set size. That's why we are doing this. Answer to your question?
Like there was some misunderstandings about this. Like as you said, like a test set is given separately in some projects and stuff.
Yes.
And I see it now. I understood
Yes.
it. Thanks for the explanation.
Yes, yes. But usually in real life, there's no contest. You just pick some data from real life, you collect data, and you do experiments. Which part is to be tested, you decided. And you should not cheat. How you do it is, you just use test for in every part. In different experiments, you use different test groups, and you do it this way. Okay. This was important, guys. This is a bit confusing because if you ask somebody what is the difference between a validation and test set, most people cannot answer it, and eventually they cannot do some valid experiments. But I hope it is settled right now. Any more questions? No. Still. But still, you can fold the validation set within the training set for better hyperparameter tuning. The folding that I mentioned was for the test set to get results from the entire set. Okay, I think that's clear now. I'm going to clean it if you don't have any other questions. Okay, I've got the parameters. here I have this cross-validation file, which we have written. Actually, we have written this part. Why we have written this part? Just like I told you, we were doing experiments with another group. Those experiments were done in MATLAB, and we need to do the experiments similarly. What I do is, what this code does is, it first loads this cross-validation file, 16. It is numbers from 0 to 15. So 0 to the 1 minus the training set minus 1. So they're in randomized order. So if I'm doing what this cross-validation function takes 3 arguments and number of the training set, which is 16. First fold, let me write them. In our case, it's 16, 1, and the fold size 4. And this code just loads a file, loads this file. This file needs to have this number of lines. It takes the first 4 for testing, because this is 1/4. So it divides the numbers, lines here into 4. It gets the first 4 for testing, the rest for the training. So that I will use the exact same test samples for this fold experiment. So anybody doing an experiment with these parameters will be using the same samples so that the experiment is statistically true. There is a MATLAB version of this file, and people are doing it the same way there. Okay? So that our experiments, fold-wise, our exclusive single fold experiments are also identical, that we could compare them. Okay. I'm hoping that this is clear, but okay. So clear. Why not clear? What is it? Okay, so at this point, it provides me test set indices, training indices, and validation indices. So let me run it and show you. So test indices is just like I told you, these. Okay, then I call another function, which again we've written from a file called dataset loader. It loads my files. Don't be fooled by the name loader, because it is not a data loader of the PyTorch, because this is going to load these values into some NumPy arrays. NumPy is the native array format of Python, as you know it. So what it does is, it goes to a folder, to this folder. It reads files up to the training size. So it reads the first 16 files in my case. Okay, let me show them together. Then it loads them using this library. I've used this library. This CO load map library has the capacity to load a MATLAB mod file into a NumPy array. Actually, it loads it to a dictionary, because you know when you put it in the workspace, it has this name input patch. So it creates a file which is in PyTorch a dictionary file. That dictionary file is this name input patch. So what I'm saying is, get the values inside that dictionary with the name input patch. So A is at this point a file with sorry, just baştan başlatım yanlış oldu. Jump edeyim oraya. So at this point, A is that file. So A is something like this. A is this. As you can see, I've loaded the files. And also I load the labels as well. So C are the labels. Sorry. C are the labels. C shape are the labels. Okay. I load all of them. I load all of them, and I append them into these input images and target masks variables. As you can see, they were empty first, but I load my entire set into these files. Then I kind of reshape them. Just let me jump here because it's a loop. I reshape them. And in the end, the target masks file is 16 by 1 by 24 by 24. That's the shape it needs to take. Okay. What I do is I calculate the channel means. Do you remember input normalization? What we said was usually before feeding to convolution neural networks, making the training set 0 input was important for us. So I make the training set 0 input by finding the mean values. If you find them, there are some values here. So TR mean, so let me show it in the variable explorer. So TR mean, it's a value, some value, as you can see here. I subtract these values from all values in all channels. So this becomes a 0 mean training set now. But I'm keeping these values. I'm going to keep these values, okay? To test them. Okay, so I return, to keep those values, I need to return these values from this function. I don't do that because this function, this code only trains it. So if you want to test it, you need to get a test sample, subtract these RGBs, and feed them to your network. Well, you may ask at this point, well, there is an input normalization layer in PyTorch already. Why do I don't use it? Again, we are trying to repeat some experiments in another framework. That's why I'm doing some part of the job by hand. Okay. So in the end, I'm converting these NumPy arrays into torch tensors because that's what I need to do. Because torch will understand only torch tensors. It still has the same shape, but it is a torch tensor now that I can feed it to my network. Okay, but that's not enough. That's not enough for the PyTorch to understand. I designate a parameter size here, the mini batch size, which is 16. I create a training set. First, using this structured data function. Structured data function is taken from dataset torch. I'm putting these values into a structure where torch will understand, can make a sense of it. So it is 2 values, images and masks. So I'm creating this structure. This is a PyTorch structure. It has 2 fields, images and masks. And I'm putting those values inside these fields, nothing else. So it becomes here structured. Okay. So I'm sending this structure to data loader. Data loader is taken from the Torch utilities library. It is going to create a data variable, which can be used by PyTorch for training. With these parameters, why do I need to feed the parameters? Look at this line. Batch size was set and batch size was 16. Since PyTorch is trying to work very efficiently, it is aligning each training set batch into some simple form so that they can be loaded easily into the GPU memory or the CPU memory. So it is like saying, get this training structure, put them in mini batch batches, mini batch sized batches. I'm going to use them. And it creates this training loader. Now we are ready to feed these values, this training set into PyTorch. And I do this for validation and test as well. As you can see, guys, this first part was manipulating my external data into a form where PyTorch can understand. And if you're doing a real problem in real world, in real data that you have collected, you will need something similar to this. If your data is in MATLAB, you can write something like this. But if your data is not in MATLAB, you must probably have to change these parts and write some other codes accordingly. But in the end, if you want to make an experiment, you'll have this experiment as well. You'll have some kind of architecture like this. Now, I create the model. When you create the model, UNET automatically calls this architecture, and these values are initialized. Okay? Good. Now, at this point, I make an initialization because in our experiments, again, when you initialize the network, when UNET creates this network in these PyTorch modules, it uses a default initialization technique. Which initialization technique? Go find Google, and then module just you in PyTorch documentation, it will explain what kind of a initialization it does. I don't want it to be how can I put it, random, because again, we were doing some experiments in parallel with other people. We want them to be the same. I'm creating a function here so that my cone layers will be initialized by the Xavier method. So store initialization so for the weights, and I'm applying it to my model. This is how you do it. Okay. Or maybe you did an experiment and you saved it, then don't initialize them. Don't use this line. Load a state dictionary for the model. It will look like this. Because if you're going to load transfer weights from another model, well, you don't have to initialize your network, right? Okay, so I either initialize or load my network. I choose my optimization scheme, which is Adam, with model parameters learning rate. With learning rate. So I choose my, I guess you know these parts because Ozan has showed you this. I'm creating a scheduler. Scheduler is like a timer function. Timer means it's going to do things periodically. So step LR is also a PyTorch function, a torch optimization LR scheduler, learning rate scheduler. I'm telling this scheduler to change the optimization parameters with these step sizes and with this gamma. So at every 5 epoch, change the learning rate by this, by multiplying with this value. So at each 5 epoch, the learning rate will be multiplied with this value. Good. And I'm asking the current working directory from the OS. So let me just, the current working directory. So if I'm going to save something, I'm going to save it here. So this is the path for my module. And I call this train model function, which I have written myself. I'm going to get into this function. And that function, you are going to recognize, guys, because train model is a function that I've taken from this train model Py. Let me show you train model Py. It's something you'll recognize. I tell it how many epochs, the model itself, the scheduler, the training set, the optimizer, the solver, which was Adam, image size, I'm going to use it for a purpose, it's 224, validation set, and the path, so that if I want to save something, I'm going to save the final model, I'm going to use it to use the path. So if you look at it, it is quite you've seen this. This is the epoch loop, this is the mini batch loop. You just get the outputs, you get the loss, you backward the outputs, starting with the loss, and you take a step where the weights are updated. I'm sure you've seen this part. This is where the training happens. So you do this for forward pass, calculate the loss, backward, you do the backward propagation, then you optimize the weights, yeah, update the weights. Then at each point, I'm saving my accuracies here, because for validation, I need to keep the accuracies. How did the accuracies work out? In a semantic segmentation problem, the accuracy, one of the evaluation metrics is the Jaccard index, which I'm not going to be talking about. It's like a classification accuracy you could think of. I'm keeping those values and I'm writing them on the screen. And I'm calling a function called validate. Validate, what validate does is, it runs the model for only forward inference. This eval means it's not going to be a training, so no grad information needs to be saved. I'm running the current state of the model. I'm sending the model here inside it. I'm running it for the validation sets, and I'm getting the validation Jaccard so that I can observe the validation. I get back. That's it, guys. When I finished, I test the model. Then I delete the model from the memory. Let's run it. Cevap vermeyince tabii. Yes. Bak, niye silmiyor bu? Ha şeydeyiz tabii ki ya, pardon. Ekranı silemedik. Okay, let us start. No GPU found, and it's going to train one by one. It's slow because I don't have a GPU, as you can see. So that's a very simple project using arbitrary data. Any questions? Okay, okay then. That's it. Then see you next week.